In this video we start our study of vectors, which proved to be a very useful technique of doing geometry in 3 dimensions. We're going to start by looking at the vector equation of a line. So, first of all, a very quick bit of terminology. The position vector of a point is simply the vector that describes the movement from the origin to the point. So for instance, if A is the point 6, 4, then the position vector of A is the vector that takes O from A, so that's the vector 6, 4. So as we can see in the diagram, the vector A, the position vector, little a, is simply the vector joining the point O to the point A. Similarly, in 3 dimensions, if B is the point 5, 2, 4, then the position vector of B is the vector little b, where O to little b is equal to the movement from O to B, which is the movement of 5 in the x direction, 2 in the y direction, and 4 in the z direction. Now, in the diagram, we have got the red line is the line y equals a half x plus 5. Now we need to observe, first of all, that the point A with coordinates 0, 5 is on the line, and secondly, that the vector 4 in the x direction and 2 in the y direction represents a movement along the line. We've also got a point P marked on the line with coordinates x, y. This is going to represent a general point on the line. Now to move from O to P, so to obtain the position vector of the point P, what we could do is first of all move from O to A, and then move from A to P. So we can say that the position vector of P, which we are writing as little r, is the same as the movement from O to A plus the movement from A to P. Now the movement from O to A is given by the position vector of the point A, which is the vector 0, 5. The movement from A to P is a movement along the line, so it must be a movement which is parallel to the vector 4, 2. And any vector that is parallel to the vector 4, 2 must simply be a multiple of 4, 2. So we can say that the vector AP is a multiple of 4, 2. We're going to call it t times 4, 2, where t is just a number. So we're able to say that the movement from O to P, that is little r, is equal to OA plus AP, so that is 0, 5 plus t times 4, 2. And this is our vector equation for the line y equals a half x plus 5. Now notice that in this equation r equals 0, 5 plus t times 4, 2. We first of all have a movement of 0, 5, which takes us from the origin onto the line. And then we have a movement which is t times 4, 2, which gives us the movement along the line from A to P. We say that the vector 4, 2 is a direction vector for the line. It's a vector which is in the same direction as that of the line. Now the vector equation of a line is certainly not unique. For example, all of the equations underneath also represent the line y equals a half x plus 5. We could have r equals 2, 6 plus t times 4, 2. So instead of moving to the point 0.5 on the line, we'd start by moving to the point 0.26 on the line. Or instead, we could say r is 0.5 plus s times 2,1. Instead of using the vector 4,2 as a direction vector for the line, we could use the vector 2,1 as a direction vector for the line. So we can see there are lots and lots of different ways of writing a vector equation for the line. Now we can generalize this argument. Consider the case of a line which we know passes through a point A, whose position vector is little a, and which has a direction vector of B. So B represents a vector in the direction of the line. Then, if R is the position vector of a general point on the line, we can again write that R, which is the movement from O to P, can be achieved by first of all moving from O to A, and then moving from A to P. Now the movement from A to P is a movement along the line, and therefore the movement from A to P must be parallel to the vector B, so that we can say that the movement A to P must be equal to t times by B, where t is just a scalar number. So we've now got the position vector of the point P, that is R, is equal to O to A plus A to P. So that is little a, the position vector of the point on the line, plus t times B. So that's plus t times the direction vector for the line. So the equation R equals A plus TB represents a straight line which passes through the point A, whose position vector is little a, and which has a direction vector of B. Now it's worth noticing that this argument that we've used here hasn't been dependent on us working in two dimensions. The equation R equals A plus TB is also valid for lines in 3 dimensions, and if you can imagine it, it's also valid for lines in 4 dimensions, 5 dimensions, or however many dimensions you want. So, for our first example, we need to find the vector equation, or a vector equation, of the line passing through the points A and B, whose coordinates are 1, 2, minus 3, and 3, 1, 2, respectively. And we also need to find the coordinates of the point where the line meets the xy plane. So a schematic diagram is worth drawing here, not an accurate 3-dimensional diagram, but just a diagram to show what's going on. So if we use A as being the point on the line that we are going to move to first of all, we've got the position vector of A is just the vector 1, 2, minus 3. The movement from A to B is 2 in the x direction, minus 1 in the y direction, and 5 in the z direction. So, for a general point on the line, we have R equals, first of all we need to move onto the line, and we've decided we're going to move onto the line at the point A. So this is going to be the movement 1, 2, minus 3, plus t times the direction vector for the line, which was 2, minus 1, 5. And remembering that R is the position vector of our arbitrary point xyz on the line, we can write this as being xyz equals 1 plus 2t, 2 minus t, minus 3 plus 5t. Now the xy plane is the plane of points which have a z coordinate of 0. Now if the z coordinate of our point on the line is 0, then we know that minus 3 plus 5t must equal 0. In other words, we know that t must be 3/5. And if t equals 3/5, then we've got r, this is the position vector of the point, is 1 plus 2t, so that's 1 plus 2 times 3/5, which is 11/5. 2 minus t, so that's 2 minus 3/5, which is 7/5. And finally, minus 3 plus 5t, which is minus 3 plus 3, which is 0. So the position vector of the required point is 11/5, 7/5, 0, which means the required point is the point 11/5, 7/5, 0. This page just shows a GeoGebra representation of the line AB that we've just found, and the point C where the line meets the xy plane has also been shown. Now the Cartesian equation of a line in 3 dimensions is rather more complicated than the vector equation, and that's the reason why most of the time we'll use the vector equation, but it is important that we know how to move from the vector equation to the Cartesian equation and vice versa. So for example, the line in the previous example was the line r equals 1, 2, minus 3 plus t times 2 minus 1, 5. If we introduce x, y and z, then we've got x, y, z equals 1, 2 minus 3 plus t times 2 minus 1, 5. In other words, we have the 3 equations, x equals 1 plus 2t, y equals 2 minus t, and z equals minus 3 plus 5t. Now we can rearrange each of these 3 equations to make t the subject of the formula. So for the first one, we can rearrange and obtain t equals x minus 1 divided by 2. For the second one, we can rearrange y equals 2 minus t to get t equals y minus 2 divided by minus 1. And the equation z equals minus 3 plus 5t can be rearranged to give t equals z plus 3 divided by 5. So we know by rearranging our equations that we have the value of x minus 1 over 2 is the same as the value of y minus 2 over minus 1, which is the same as the value of z plus 3 divided by 5, and all of those are equal to t. So we now have a Cartesian equation for the line 1, 2 minus 3 plus t times 2 minus 1, 5, and that Cartesian equation is x minus 1 over 2 equals y minus 2 over minus 1 plus z plus 3 over 5. If we are given the Cartesian equation for a line, then it is fairly easy to reverse the process and find a vector equation for the line. We know that the fractions x minus 4 over 2, y plus 5 over minus 3 and z equals 2 have got a common value. Let's call that common value t, in which case we can say that x is 4 plus 2t, that y is minus 5 minus 3t, and that z is 2t. In other words, the position vector xyz of our arbitrary point is given by 4 plus 2t minus 5 minus 3t 2t, where t is our arbitrary number. And we can rewrite that equation as r equals 4 minus 5, 0, plus t times 2 minus 3, 2, which is our vector equation for the line. In general, the line whose vector equation is r equals a1, a2, a3 plus t times b1, b2, b3 has Cartesian equation x minus a1 divided by b1 equals y minus a2 divided by b2 equals z minus a3 divided by b3, and each of those values is actually equal to the number t in the vector equation. And it's worth noticing that the numbers being subtracted in the numerators of the Cartesian representation are the coordinates of the known point A on the line, whilst the denominators of the three fractions are the components of the direction vector of the line. Now we need to consider the intersection of lines in 3 dimensions. So let's imagine that we've got a cuboid as shown in the diagram, and we consider 1 or 2 lines formed by edges of that cuboid. So if we have the lines RS and LR, they clearly intersect at the point R. If, on the other hand, we have the lines RL and SM, they won't intersect because they're parallel lines. And finally, for this little example, if we have the lines KM and PR, the lines are certainly not parallel to each other, but they don't intersect either. And it's clear that they won't intersect because the line KM is a line which is on the plane formed by the base of the cuboid, whereas the line PR is a line which is in the plane defined by the top of the cuboid. Lines like KM and PR are called skew lines. And skew lines are lines which are not parallel and which do not intersect. If we are given 2 lines, then the first thing it is sensible to do is to see whether the 2 lines are parallel or not. And for the 2 lines to be parallel, the direction vectors must be parallel to each other. And this will be the case if the direction vector of one of the lines is simply a multiple of the direction vector of the other line. Now, if we're given 2 non-parallel lines, then the strategy we use to decide whether those 2 lines are intersecting lines or skew lines is to find values of the parameters s and t so that that 2 of the coordinates of each line are equal. For example, we might find the values of s and t so that x1 is equal to x2 and y1 is equal to y2. We might instead find values of s and t so that x1 equals x2 and z1 equals z2. Or we could find the values of s and t so that y1 was equal to y2 and z1 equals z2. Once we've found those values of s and t, we then use the 3rd coordinate to decide on whether the lines are intersecting lines or skew lines. If the third coordinates are equal to each other, then the two lines are intersecting lines. On the other hand, if the third coordinates of the lines are different, then the lines must be skew lines. So let's see all of this in practice with an example. We have to determine whether the following lines intersect, are parallel or askew. And we're going to start off with the lines L1 and L2. So we can straight away see that L1 and L2 are not parallel because the direction vector for L2 is the vector 2, 1, 1, which is certainly not a multiple of the direction vector for L1, which is 1 minus 2, 1. So we certainly know that the two lines aren't parallel. So let's now try and find values of s and t which will make the x-coordinate of L1 equal to the x-coordinate of L2, which requires 1 plus s to be the same as minus 2 plus 2t, and we're also going to try and find values of s and t which will make the y-coordinate of L1 equal to the y-coordinate of L2. And that will require minus 2 minus 2s to be equal to minus 6 plus t. Rewriting those simultaneous equations into rather more friendly format, we have s minus 2t must be minus 3, and we have minus 2s minus t must be minus 4. And solving those simultaneous equations using a standard method, or indeed using your calculator, will give me s equals 1 and t equals 2. So when s equals 1 and t equals 2, we've got the z coordinate of line 1 is equal to 0 plus s, so that is just equal to 1. Whereas the z coordinate of line 2 is minus 1 plus t, so that's minus 1 plus 2, which is also equal to 1. So we've got z1 equals z2, so the lines certainly intersect, and if we substitute in s equals 1 and t equals 2, we can check that this is indeed the case. We've got the lines intersect at the point where x equals 2, y equals minus 4, and z equals 1. So we have the point of intersection is the point 2, minus 4, 1. Now if we move on to the lines L1 and L3, we can see that the direction vector for L3 is the vector minus 2, 4, minus 2, which is minus 2 times the direction vector for line L1. So this tells us that the direction vectors of L1 and L3 are parallel, so the lines L1 and L3 are parallel. What's more, if we have a think about the point 4, 1, 1, there is no way that the point 4, 1, 1 can be written as a point on the line L1. There's no value of s such that 4, 1, 1 is equal to 1 minus 2, 0 plus s times 1 minus 2, 1. And this means that the point 4, 1, 1 is definitely not on the line L1, which means that the lines L1 and L3 are parallel but definitely distinct. They're not the same line. Finally, let's consider the lines L2 and L3. First of all, the lines aren't parallel because we can't find a value of k, so that minus 2, 4, minus 2, which is the direction vector of L3, is a multiple of 2, 1, 1, which is the direction vector of L2. So the lines are certainly not parallel. So let's now try and find values of t and u so that the x-coordinate of L2 equals the x-coordinate of L3, and also the y-coordinate of L2 equals the y-coordinate of L3. So x2 equals x3 gives me minus 2 plus 2t equals 4 minus 2u, which can be tidied up to 2u plus 2t equals 6. y2 equals y3 gives me minus 6 plus t equals 1 plus 4u, which tidies up to 4u minus t equals minus 7. Solving those simultaneous equations gives me u equals minus 0.8 and t equals 3.8. Now if I have t equals 3.8 and u equals minus 0.8, then I've got x2 is minus 2 plus 2t, which is 5.6. y2 is minus 6 plus t, which is minus 2.2. z2 is minus 1 plus t, which is 2.8. On the other hand, x3 is 4 minus 2u, which is 5.6. y3 is 1 plus 4u, which is minus 2.2. And z3 is 1 minus 2u, which is 2.6. Notice that z2 is not equal to z3, and that is quite enough to tell us that the lines must be skew lines. Now at this stage I'd like you just to pause the video and have a go at this one question, which really takes us through all of the work that we've had a look at in the course of this video. So stop the video at this point and have a go at the question. Now there's just one last point I want to make on this video, and this is a question of notation more than anything else. We've been using column vectors to write our three-dimensional vectors and indeed our two-dimensional vectors. When we're trying to print vectors, it's very useful to have a shorthand which doesn't require 3 lines of print. So we introduce the vectors I, which is the vector 1, 0, 0, the vector j, which is the vector 0, 1, 0, and the vector k, which is the vector 0, 0, 1. Now if we do that, then we have geometrically the vector I is a movement of 1 unit in the x direction, vector j is a movement of 1 unit in the y direction, and the vector k is a movement of 1 unit in the z direction. Now, if we've got the vector 4, 3, 5, with a little bit of thought, we can see that the vector 4, 3, 5 can be written as 4, 0, 0 plus 0, 3, 0 plus 0, 0, 5. In other words, it's 4 times 1, 0, 0 plus 3 times 0, 1, 0 plus 5 times 0, 0, 1. So in other words, we can write the vector 4, 3, 5 as the vector 4i plus 3j plus 5k. Equally well, the vector 7i minus 2j minus 3k is a useful way for printers and in books to write the vector that we would normally write as the column vector 7 minus 2 minus 3. Now you are expected to be familiar with this IJK notation. It isn't difficult, but it is sometimes used in exam papers simply because it's more efficient in terms of paper usage. And that finishes our first video on vectors.